Hi, Alex here again. Now this part we will be looking at the design of shaft based on the failure of shaft due to combined bending and twisting. So first, we have maximum shear stress theory or gas theory. And this is the formula that we use for maximum shear stress theory. That is the maximum shear stress. This is the bending stress. And this is the shear stress due to twisting moment. Then we have maximum principal stress theory or the Rankine's theory. And this is the formula that we use: bending stress and shear stress. So this is the maximum normal stress or the maximum principal stress for the design of the shaft when it is subjected to both bending and shearing. Take note, maximum shear stress theory or gas theory, it is actually used for ductile materials such as mild steel. And the maximum normal stress theory or the maximum principal stress theory, or sometimes it's known as the Rankine's theory, it is used for brittle materials such as cast iron. Now, here we will be looking at the maximum shear stress theory first, or gas theory. So this is the formula that we have earlier, and we know that this is the bending stress, and this is the shear stress on the shaft due to twisting moment. So sigma B is actually equal to 32 m over pi d cubed, and shear stress is equal to 16 t over pi d cubed, which we have done both of these earlier. So m here, it refers to the maximum bending moment or the bending moment. The t is referring to the twisting moment or the torque. So this is our maximum shear stress theory, the formula, where we have substituted the sigma b and the shear stress for the sigma b and the tau s. So we have this equation here. So the next we have 4. Now we can consider the 4 as actually 2 to the power of 2. Then we can put in the 2 to the power of 2 into the bracket. So you have 2 to the power of 2 here. So then tau max is equal to half square root of 32 m over pi d cubed square plus 32 t over pi d cubed square. So we can extract the 32 over pi d cubed from the m square and the t square. Okay, then 32 cancel off with the 2, so you have a 16. Okay, so if when we bring this section here, or this part here, 16 over pi d cubed over to the left hand side, then we have pi d cubed over 16 times tau max is equals to the square root of m square plus t square. So once we have got this equation here, we can introduce a term which we call TE, or the equivalent twisting moment, to be equals to the pi over 16 d cubed times tau max, or TE can also be equals to the square root of m square plus t square. Okay, so that is TE equals to square root of m square plus t square, and TE is equals to pi over 16 d cubed times tau max. So now what you have to do here, the first thing is to find out the maximum bending moment, or the moment at any given section, and also the torque or the twisting moment. Then you will be able to find out the TE. Once you have got the TE, then based on the questions, if tau max or the maximum shear stress is given, then we can put it into this equation in order to find the diameter of the shaft. Now, then the next part is the Rankine's theory, or sometimes it's known as the maximum normal stress or principal stress theory. So you have sigma max and then half sigma b plus half square root of sigma b square plus 4 tau s square. That is your shear stress. So, and we know that sigma b is equal to 32 m over pi d cubed, and the shear stress is equal to 16 t over pi d cubed. Then substitute sigma b, please. and the shear stress into this. So you will come to this formula or equation here. So you can see 32 over pi d cube, 32 over pi d cube. The only thing is this section is not 32 over pi d cube. But what we can do with the 4, that is to rewrite this as 2 to the power, rewriting it as 2 to the power of 2. Then you can bring the 2 to the power of 2 into the bracket after that. So you have 2 times 16, that is actually the 2 power of 2 here. So 2 times 16 now becomes 32. So from here you can see the common part of this equation is that the 32 pi d cube, 32 pi d cube, and the 32 pi d cube. So from the within the square root, extract this 32 over pi d cube out. So you have this square of 32 over pi d cube on both sides. So then remaining m square plus t square in the bracket. So you can take this out from the square root. So you have 32 over pi d cube. So as you can see now, there's a common of 32 pi d cube and 32 pi d cube. So once you extract this, you have 32 over pi d cube. Sorry, this is not a plus, it's a multiply sign. Should be a multiply sign. So the half, the m, and the square root of m squared plus t squared. Then what you need to do is this is times, okay? So bring this 32 over pi d cube to the other side. So you have pi d cube over 32 times the sigma max. This part and this part. Then we introduce the term ME, which is the equivalent bending moment, to be equals to pi over 32 d cube times sigma max, or also can be equals to half m plus square root of m squared plus t squared. So now what you need to do is just the same as what we have earlier, based on the maximum shear stress theory. Find out the maximum bending moment first, or the torque, then you find ME. Once you have found ME, and with the given normal stress, maximum normal stress, or the maximum bending stress in a question, you will be able to find out the diameter of the shaft. And that's all for this section. Thank you very much for watching. And if you have any questions, you can put on the comment section of my YouTube channel under the section of the design of shaft. Thank you very much. Bye bye. See you again. Thanks. Bye.